All right, now when we look at this arc of charge and say, well, how am I going to handle this problem? Well, I'm going to handle this problem just like I handled all the other ones. So when I look here, I've got my basic formula for a point charge, and we got 1 over 4 pi epsilon naught q divided by r squared. Isn't that our basic point charge formula? All right, now the question is, what does ds, how much contribution do we get from that? Well, if we look there, a little bit of segment of ds is going to give us a little charge dq. And this little segment down here, ds, is going to give us a little bit of charge. How much? dq. All right, so let's rewrite the formula just like we've been doing. And now we're getting a little bit of electric field created by dq. So what is that electric field? And the answer, of course, is going to be a little bit of dE, a little bit of electric field. So I'm now going to replace q with dq because that's our charge, and then we're dividing it by r squared, like so. All right, now we've got a problem with the dq, of course. We don't really like dq because it's very hard to measure a very, very tiny bit of charge. I mean, how do you actually do that? And the answer is you really can't. All right, so let's take a look at the densities. So density, of course, is our link here. Now, if we look here, the density of this ring is going to be the total charge of the ring. Now, remember, the charge of this ring is negative this time. Why? Because we made it so. All right, divided by, well, now, if we divide this by the length, so if I'm using length linear density, can you imagine this arc going all the way around? Well, if it goes all the way around, it's going to end up being 2 pi r in size. All right, now, but it's not all the way around. How far is, let's see, from 60 to 0 plus 0 to negative 60? Isn't that 120 degrees? Yeah, it is. All right, see, 360 in a circle, 120 degrees for this arc. It looks to me like the amount of length of this arc is going to be only 1/3 of the circumference. So if we look here, we're going to have to multiply, or actually I guess divide this by 3. So this is going to end up being our density. Now, we don't necessarily want the entire density of it. If we're looking here, we really want dq to get rid of that. So if I take a little sliver of it, I have dq divided by, well, how big are these little segments? And the answer is ds again. Boy, this looks familiar. We've done this before. So let's write this down. So we've got dE is equal to 1 over 4 pi EL. And instead of writing dq down, isn't dq going to be lambda times ds? So let's write that in there. So we've got lambda times ds r squared, like so. All right, now, we've got a little bit of an issue here. This is the basic formula for dE, and that gives us the hypotenuse of that triangle. All right, but remember, these things are on angles. We've got to make a correction here because the only part that contributes to the electric field is the part that's going towards the arc. Remember that this portion is dE cosine of the angle. So we've got dE here. To get the actual total electric field, don't we have to put in this, the cosine of the angle, like so? So as we look at this, we've got the cosine of the angle as a correction just to give us the ones that truly count, not the ones that are going up and then cancel out downward. So we've got ourselves a revamped formula here, which is very nicely done.